This is section 12.7, part 2, and we're going to be looking at differentials. The differential is actually pretty closely related to the idea of the linear approximation, but instead of actually calculating an approximation for a new z-value, instead it just calculates the change or the approximation to the change in the z-value. So once again, if we imagine we've got a surface here, this ellipsoid, and I've got a tangent plane, which serves as the linear approximation to that ellipsoid at some point of tangency, right here, it's perfect. Then if we imagine that we move over a little bit, and again I'm going to move over more than I would normally, to say another point over here, then the actual z-value has changed by some amount. Right? Here's the old z-value, here's the new z-value. This would be called delta z, the amount of change in z. And the actual change would just be f of the new x and y values, x plus delta x, y plus delta y, minus the z-value originally, f of x, y. Now, in many cases, that's a relatively complicated thing to calculate if you don't have a calculation device. So once again, we're going to say, is there a way to approximate it? In order to do that, we say, well, instead of using the actual new z-value, right, we use the z-value up here on the tangent plane instead. And that change is called dy, the differential. So dy, the approximate change, or the change on the tangent plane, approximates delta z, the actual change in z on the surface. Calculating dy is done by taking the partial derivative f sub x times the change in x dx plus the partial derivative f sub y times the change in y, which we'll usually call dy. All right, let's take a look at, actually it should be a familiar problem. We've already done a linear approximation. We're now just going to look at it from a different perspective, the perspective of differentials. And we're going to say, let's start with the function z is equal to x squared plus y squared. And we'd like to use the method of differentials to approximate the change in z when we move from the point 3,4 to the point 3.06, 4.1. So again, notice it's the same function and the same final point that I'm really ending at here, 3.06, 4.1. So we should get something kind of similar happening. All right, so let's see here. In order to do dz, I'm going to need f sub x and f sub y, so let's get those first. F sub x, or z sub x, would be 1/2 x squared plus y squared to the negative 1/2 times 2x, or x over the square root of x squared plus y squared. And if I plug in my point, my starting point, which was 3,4, 3 on the top, and the square root of 9 plus 16 is the square root of 25, so that would just be 5 on the bottom. F sub y, or z sub y, almost the same derivative. Chain rule just gives me a 2y this time instead. So once the 2's cancel, I just end up with y over the radical. And again, I'm going to plug in my point, 3,4, to get 4/5 for f sub y. dx is the same as the change in x. And if I look at my point, it's pretty clear it's 0.06. I'll write it out just in case you want to look back sometime, but the new x minus the old x, 0.06 in this case. And the same thing for dy. dy is just the change in y. So that would be 4.1 minus 4, or 0.1. All right, to get our differential, our approximation for the change in z, we're going to take our f sub x, 3/5, times the dx, 0.06, plus f sub y, 4/5, times dy, 0.1. And you could just do that on a calculator. Uh, 0.116. So before we go on any further, I just want to remind you that that's very consistent with what we were doing with the linear approximation. Remember that when you actually plug 3 and 4 into this problem, you would get square root of 9 plus 16, which is 5. The change is 0.116. And remember, the linear approximation we got on the previous page was 5.116. So these pieces are very, very much related. We were supposed to compare this to the actual change in z for these same values. So our actual change in z would be f of the new point minus f of the old point so the square root of 3.06 squared plus 4.1 squared minus the square root of 3 squared plus 4 squared, which is definitely a calculator problem, right? If I really had to, I could have done this one by writing it out, but this one I really wouldn't want to do any other way. And I end up, oops, if I can get that so you can see it, you can probably see I ended up getting 0.116014 blah, blah, blah. So it's very, very close. That would, of course, continue. And you can see that these two numbers are very close. This is an excellent approximation. All right, let's take a look at one application where we might use something like differentials. Again, this is what happens when we want a kind of a quick estimate of something, and it's really commonly used to estimate small changes in things. So here we have a cone of radius 6 and height 4.2, and I'd like to approximate the change in volume if the radius goes up to 6.05 centimeters and the height decreases to 4.12 centimeters. We could then compare that to the actual change in volume. So first of all, we are talking about the volume of the cone. So let's start by writing down our volume formula for a cone. 1/3 pi r squared h. And in this case, instead of my variables being x and y, my variables are r and h. So the differential dv would be v sub r dr plus v sub h dh, right? Just like the x's and the y's, just for the variables in this particular problem. So let's go ahead and calculate those. V sub r would be 2/3 pi RH. And if I were to plug in my 6 and my 4.2, I'm going to keep quite a few decimal places here. I'm going to get about 52.77876. dr, my change in r would be 6.05 minus 6, or 0.05. And then we need v sub h. Derivative with respect to h, that h is just going to take, the derivative is going to become 1, so I'll just get a 1/3 pi r squared. And again, when we plug in at this point, we always plug in our original values. So I'm going to plug in the 6 for the r. And again, just to make this a little easier to substitute, I'm going to get a decimal value, but I'm going to keep quite a few decimal places. And I'm getting a 37.69911. Finally, dh is our new h value, 4.12, minus the old one, 4.2, which would be negative 0.08. All right, let's just plug everything in, and we'll have it. So dv is going to be about negative 0.377 approximately. And that's a change in volume, so in this case that would be cubic centimeters. So we're saying that although the radius increased, because of the decrease in height, apparently we actually end up with a smaller volume than what we started with. We could, of course, compare that to the actual change in volume, delta V, which would be the volume at 6.05 and 4.12 minus the volume at 6 and 4.2. So I'd get a 1/3 pi times that radius squared times that height. And we would subtract a 1/3 pi times 6 squared times 4.2 squared. And that will actually give us our true change in volume. Oops, sorry, that was the height. That shouldn't have been squared, should it? My fault. There we go. So this minus that gave me about negative 0.416 cubic centimeters. And you can see that, again, we're not too far off, a few hundredths, in our approximation. All right, so that brings us to the end of 12.7.